Now we're on to properties of a system. Now, as a note, when you're doing this, going through thermodynamics, notation is pretty important. Mostly for when you are reading what's happening in the question and also when you're reading your textbook. Because I don't really care what you write for velocity, volume, mass, temperature. You can use your own crazy language if you wanted to. You could make up squiggle marks if you wanted to. That could be volume for you. And that's fine. But your book doesn't do that. And it does things very, very specifically. And so we have to make sure that we're using it and doing it in the right way. So let's try this out. First off, what is a property? A property is simply any characteristic of a system like mass, volume, temperature, pressure, density. All of those are things that I'm going to be measuring from a system. They're macroscopic things that I can actually measure rather than microscopic things that I can't actually look at. Now, you're used to these guys. Ones you're probably not as used to. We're going to be going through this semester like enthalpy, internal energy, entropy, exergy. Those are the other things we're going to have to deal with. We'll figure out those and we'll explain them as we get to them. Now, these properties are either going to be intensive or extensive. What do we mean by that? Well, an intensive property is those that are independent of the mass of a system, like temperature, pressure, and density. So they don't increase if I increase the mass, so long as everything else is allowed to move. Like, for example, temperature, pressure, and density. If I were to double the amount of mass here, the temperature is not going to just suddenly change because I doubled the amount of mass. If I double the amount of mass here and also double the volume, the pressure is not going to change. And also, if I have a particular amount of mass, I won't have, based on that mass, a particular amount of temperature, or a particular amount of pressure or density. So they are disconnected. Extensive are those that depend on the size of the system. Now, which ones depend on the size of the system? Well, guess what? Mass does. The bigger the system I have for a particular set density, the more mass I have. The bigger a system I have, well, obviously, the more volume I have. So those are extensive properties, okay? Those are extensive properties. Now, how do I tell that? Well, look at this right here. So this particular system, remember, I have a boundary, that's a system. I divide it in half with this imaginary boundary. And what I'm going to notice is that the temperature, pressure, and density on both sides are the same. They didn't change because we halved it, even though we're halving it in our heads. That's because they're intensive properties. They're not connected to the mass. They don't care about the size of the system. Now, extensive properties, though, well, when I split this in half my mass is on one side and half my mass is on the other. Half my volume is on one side and half my volume is on the other. So they have been split. So the size of my system matters for those properties. They're going to get bigger or smaller depending on what the size is. The last little detail, which is incredibly important, is specific properties. These are extensive properties that are per unit mass. And what you're going to see throughout the entirety of the textbook is they're always shown with a lowercase letter. So this guy right here is an extensive property. This is E, that's energy. And when I divide it by mass, it becomes a specific property, which is specific energy. It's specific to mass. So the more mass I have, the more energy I have, but this is helping me normalize it by a per unit mass. And same thing right here. This is specific volume. You're going to see these a lot, so know when you see a lowercase letter that that is per unit mass. Why? Because sometimes we're dealing with things like mass flow, and we need to put things on a per unit mass basis to be able to solve the problems. Okay, I think that's it for this time. Oh, we got a little more. One last little detail. And this is just helping us to understand an assumption that's being made. Now, like I said before, everything you deal with is coming from microscopic properties, okay? I have water, it's bouncing around. That gives me temperature, pressure, the amount of water molecules I have, gives me density. All of that is coming from something that is microscopic that I cannot see. I can't see those things. And so we don't deal with them. We deal with macroscopic properties. But when we're dealing with macroscopic properties, one thing we have to think about is that there's actually a whole lot of empty space in between these molecules, even if I have high densities. Even with liquid water, there's still space in between the molecules. It's a lot less than. But with air, there's a whole bunch of space between those molecules. But we don't treat things as if there's any gaps. Instead, we say it's a continuum, which is simply saying that the area that we're looking at, our system, remember the system we are drawing here, is simply completely perfectly filled, no gaps whatsoever. And so it's continuous and homogeneous matter. There are holes in real life. We're not thinking about those holes, and it's not going to affect our calculations when we're looking at the sizes, the scales we're looking at. If I was zooming in on an absolutely tiny volume, it would matter. I would have to treat it as, individual particles. But when I'm looking at a very large system, which 1 cubic inch, 1 tiny inch is a large system, then I can treat it as a continuum. So it's completely homogeneous. So this is a basic assumption we're making the entire semester. You don't have to write it down or anything, but just know that we're always dealing with it that way. Okay, so next time, examples. So let's try it out next time, and I'll see you later. Have a great day. Bye-bye.